Alright, here we are back talking about geological layers and so forth, and we're talking about unconformities, okay? Things that don't match up when there are gaps in the record that are things that are missing, okay? And the first type of unconformity we're going to talk about is an angular unconformity. An angular unconformity is probably one of the easiest ones to identify. If we look at a layer of rocks like this one up here, and we can see obviously that these rocks at some point were tilted, then it all eroded across, pin back, all right, and something eroded them down, and then layers were starting to deposit back on top of them again. Well, obviously there's some time passed in there where these were tilted and the time that they got eroded, and then things were started to be deposited on them. So that would be an example of an angular unconformity, okay? For example, in this picture over here, if you had sediments being deposited underwater, like in a shallow ocean or something, okay, the water's receded, and now there was either uplift, something pushed these up, they were being compressed perhaps, and therefore folded, and so you have these layers, okay, and it becomes more of a mountainy, hilly terrain, because you've got these hills and everything, all right. As it erodes, it gradually flattens back out, and then say it becomes back underwater again, and you get layers back deposited on it again, okay, and so there would be a passage of time here, this time when it's above water and being eroded and stuff, that is not going to show up on here because nothing was being deposited. Things are being lifted up, things are being carried off somewhere else to be deposited, and now things are being deposited again. So an angular unconformity like this one over here, or like demonstrated over here, demonstrates how there's a missing period of time in that point. And most places on Earth, we're not going to have a solid continual time unless they were constantly under the water, or in an area where things are being deposited or sediments are being deposited on a regular basis. Are they going to have this nice solid record? There's going to be unconformities, and this would be an example of one. So angular unconformity is where you see an angle and then there's flat rocks been deposited on top of them. A nonconformity, okay, nonconformity means there's things that don't match. For example, if these granite layers were to be shoved up into the air, so you have a great layer of say igneous rock that was shoved up from underground, okay, it may have formed many years ago. Well, eventually it may get eroded, okay, and so this gets off here and maybe okay, and it gets eroded off, and maybe other things get deposited, and then eventually you start getting layers up on top of this layer. Well, these two layers are right next to each other, but this was a very old layer that was down inside the earth. Now it's been shoved up to the surface, and new layers are being stacked on top of it. There's a time gap or discontinuity or non-conformity. It doesn't match. They don't match. Normally we say, well, the layer right on top of it would just be a little bit newer, but there's a big time difference between these two, not to mention allowing for all the erosion and other things that have happened. So that would be a non-conformity. All right, a third type would be a disconformity. Okay, we've got unconformity, nonconformity, and now a disconformity. Okay, but a disconformity is probably the hardest one to calculate. So we have layers that are laid. This is laid down first. This one's laid down second. Woo, high math. Again, it always gets me. Fourth layer up here. Okay, and say the fifth layer. But say the ocean dries up, and now we begin to have erosion, and some of this is wiped away. Okay, and so these top two layers, let's just say they get wiped off. Okay, but the ocean moves back in and it begins to deposit. Well, this is not the same time as layer 4 would have been. This would be, in time, we'd say 6, okay? And then the next layer on top of it is 7. So there's a gap right here between what used to be layers 4 and 5 were deposited and then got eroded away. So there's a difference in time between layer 3 and number 6. They are not, once again, 6 is not just slightly older than 3. There's a gap of several layers in there, and maybe a fairly considerable amount of time there. All right. Now the difficulty with this is you don't have the obviously angled rocks that have been smoothed off. Okay. Here you don't have an obviously different rock formation like the igneous that's been shoved up into there. So you think, hey, something might not be the same here. Okay. Here you just have layers and layers, and if you're not careful, these would obviously look as though they were just continuous, and that this one was laid down, then this one, and right after layer 3 was layer 7, where in fact there is a gap there. Okay. Now, one of the ways we would try to watch for that would be trying to look for over here, like we talked about earlier. We'd go someplace else and try to find layers that match up with it somewhere else. And if there's some layers over here that don't show up over here, then maybe we say, hey, maybe that's where those layers were, and they were here, but they got eroded. But as you can see, this is not an exact science. There's room for well, maybe it's not exactly. It's not an exact science. Anytime you go far back in the future or start trying to predict out in the future the other direction, you go back in the past. Go back in the past too far, or go out in the future too far. The amount of certainty with which we can say what happened or what might have happened obviously begins to drop. Okay, and that's certainly true in geology. You'll hear scientists talking about, well, this happened, and this happened, and this happened. Well, that's what we think, and yes, we have evidence for it, but that's not saying that necessarily it's correct. And the farther back in the past or farther out in the future we predict what will happen, then the less we can do that. Now, all of this we've been talking about are relative dating. You have these different layers, okay, and you say which ones are older, which ones are younger, some unconformities that show that there's some gaps or missing points in there, okay, but none of these actually tell us that this is so many million years old, okay, or something like that. Okay, and so how do we do that? Well, we've talked about it a little bit earlier when we talked about isotopes and radioactivity and what it's used for, but the biggest answer would be radiometric dating. Okay, and radio just has to do with radioactivity in this case. Okay, not that you should date radioactive people. That's not it. That's okay. Or radios for that matter. Metric means to measure. So we're using radioactivity to measure the date of these rock layers. Okay, and basically we take the radioactive isotopes, okay, of certain elements, and we measure how much of their decay products are present, and so we figure out how much of the isotope there was originally, how much of the decay product is left or have been formed. Okay, let me try that again. How much radioactive isotope is left, how much decay products have been formed, and then by using that information we will try to predict how long it has been, how old this rock layer has been around. Okay, now we're assuming that the radioisotope started breaking down when it was formed. Once again, what if it melted? What if it was under heat and stress? How would that have affected those isotopes? Would it have affected those isotopes? It may have. Okay, but as far as we know, it seems to be fairly consistent how quickly. And if you remember the half-life, we use half-lives, and half-lives tells us how long does it take for half of it. So if we found half of the equal amounts of radioactive isotope and the decay product, that would mean half of it has changed into the decay product. So you have half and half of each one, and that would be one half-life. Okay, and whatever the half-life of that isotope is, that's how old these rocks would be dated to be and be considered to be. Okay. Alright, now we got the right screen how we want to look at it. Basically, if this is how much there was the isotope left, the time it would take for half of it to be gone and to be broken down into the decay product would be one half-life, and then it would just depend how long the half-life was for that particular element. Okay, that half would have broken down into a fourth. So if we had 1/4 of the isotope and 3/4 or 3 times as much of the decay product, we would know it has undergone 2 half-lives. In 3 half-lives, it would be 1/8 of the isotope present, but there would be 7/8 of the decay product, and so on and so on, and it would keep going down there. Now, we talked about a little bit, but let's just go over it again. Depending what kind of element we have, uranium 238, okay, breaks down into lead 206. So you would take these two atoms, see how much you have of each one, and if you had half and half, then that means it would be 4.5 billion years ago. Okay, uranium 235 breaks down into lead 207. It's only 704 million years for a half-life. Potassium 40, which we have in our bodies, breaks down to argon 40. It takes about 1.3 billion years. Okay, so it would be a pretty good one. So for long rocks, we would use isotopes like this, uranium and potassium, that are in there. For shorter time periods, things that have been alive and have put carbon in their body, because all living things we know are made out of organic compounds and have carbon in them. We look at the carbon-14. It breaks down over time into nitrogen-14, and its half-life, for half of it to break down, takes about 5,000 years. And so eventually you would get to where there's so little left of the carbon that you wouldn't be able to measure. So usually for rock layers, we're using things like these that take millions or billions of years to break down into a half-life product. Okay. Now, is this give us an exact time? Oh, that's exactly 8 billion years, 3 months, and 2 days. No, and there's a plus or minus so many million years. So once again, not an exact science, but it's something that gives us an idea, and certainly can tell us if this rock is older than that rock, and gives us an idea of, it's still their relative age, but a lot more specific. Okay, and so we do radiometric dating with the isotopes and so forth. That gives us a lot better age of how old the rocks are. And that's it for chapter 29. Relatively quick chapter.